In this video, we're going to think a little bit more about linear combinations, and we're going to introduce the idea of a span and of a spanning sequence, which is, again, actually something we've already seen. So beginning with the definition of a span. If you have a vector space V and some vectors or some elements v1 up to vn belonging to V, then the span of v1 up to vn, which we write like this, just means the set of all linear combinations of v1 up to vn. So in symbols, you could write it like this. And this is a concept we've already seen before, because we talked about the column space of a matrix. And the column space of a matrix was defined to be the set of all linear combinations of the columns of that matrix. In other words, the span of the columns of that matrix. You'll remember that it was useful to us because we showed that you could solve a matrix equation AX equals B if and only if B belonged to the column space of that matrix. In other words, to the span of the columns of the matrix. So let's take a look at some examples and some special cases to get the hang of what this definition is talking about. So let's look about the special case, what happens when n equals 1. Well, when n equals 1, you've got one vector v1 belonging to a vector space V. And the span would be all the linear combinations of that one vector. But a linear combination with just one vector in it is just a scalar multiple of that vector. So the span of a single vector V would simply be the set of all scalar multiples of V. So lambda would belong to the field over which V was a vector space. And this is something with a nice geometric meaning, like a lot of the concepts that we develop in linear algebra. Because if you took, for example, a vector in R squared, so for example, let's say V is going to be 1, 1, an element of the vector space R squared, then span of this vector V will be the set of all scalar multiples of that vector. And a scalar multiple of V, so A times V, is just the vector A, where A is any real number. So if you like to think geometrically, then you could draw a picture of what's going on here. I mean, if we just draw some axes like this, then what we've got just there is we've just worked out that the span of this vector V was actually this line like this, line through the origin. So that red line is continuing on in both directions, of course, infinitely, is this span. Okay, let's think about another example of a span just while we're on this definition slide. So let's take two more vectors inside R squared. So let's let V1 be the vector 1, 0 and V2 be the vector 0, 1. So what is then the span of V1 and V2? So those two are elements of the vector space R squared again, and the question is what can we say about, how can we describe the span of V1 and V2? Maybe pause the video and think about it. Okay, well the answer is that the span is all of R squared. Let's write this in a slightly nicer way. Span of V1 and V2 is all of R squared, because any element in R squared can be written like this, and that is equal to a linear combination of V1 and V2. It's x times V1 plus y times V2. Okay, every element of R squared can be written as a linear combination of V1 and V2. So the span of V1 and V2, which consists of all the linear combinations of V1 and V2, that's all of R squared. So let's prove a general result now about subspaces. In fact, I'm not going to prove this result because we've essentially already done it in our video on null space and column space. We proved that the column space was a subspace, And of course the column space is defined as a span, and exactly the same proof works. So all I want to say here is proof, this is exactly the same as the proof that the column space of a matrix was a subspace of R to the M from our lecture on null space and column space. So if you'd like to see the proof written down in this general case, then you can look up the proof in the notes. So this proposition 4.7.1, it's got a complete proof as usual in the lecture notes for Math 5. And you can look it up there. So at the end of our examples of spanning sequence, the end of our examples of spans, we noticed that if you took the vectors v1 is the vector 1, 0, and v2 is the vector 0, 1 inside r squared, then their span was the whole of r squared. And that property has a name. It's called the property of being a spanning sequence. So the general definition is that if you've got a sequence of elements v1, v2 up to vn in a vector space v, then you say that they are a spanning sequence for v if and only if their span is equal to the whole of v. So every linear combination in v, every vector in v can be written as a linear combination of v1 up to vn. So let's see some other examples of this. We've already seen, but I'm going to copy it here, that 1, 0 followed by 0, 1 is a spanning sequence for r squared. Okay, let's now take another example. So let's stick with r squared, but take some different vectors. So this time, let's take u1 is going to be the vector 1, 1, and u2 is going to be the vector 1, minus 1. Then I claim that u1 and u2 are a spanning sequence for r squared. In other words, I claim that every vector in r squared is equal to a linear combination of u1 and u2. So if we prove this, then we will have proved that u1 and u2 are a spanning sequence for v. And actually, this question is just a simultaneous linear equation problem in disguise. This is simply an example of some simultaneous linear equations, and so you can solve this and all problems like it just using what you already know about how to solve systems of linear equations. So let's add this as a comment because it's so important. This is just a matrix equation problem in disguise. So why is that? Well, if you want to show that span is equal to r squared, you have to show that every element of r squared is equal to a linear combination of u1 and u2. So let's pick an arbitrary element of r squared. We'll call it the vector xy. And we want to show that there are scalars, so alpha and beta, real numbers such that alpha u1 plus beta u2 is equal to xy. Okay, in other words, that 1, 1, 1 minus 1 multiplied into the vector alpha beta is equal to xy. You're trying to show that this matrix equation always has a solution. If you're not quite sure why this matrix equation is equivalent to saying that alpha u1 plus beta u2 is equal to xy, remember what we learned about multiplying matrices into column vectors. If you multiply a matrix into a column vector, that's the same as taking a linear combination of the columns of the matrix. So in this matrix multiplication here, you get alpha times the first column, that's alpha times u1, plus beta times the second column, which is beta times u2. So the left-hand side of that matrix equation really is alpha u1 plus beta u2. Okay, you want to solve this? Well, you can just do it. You can use your you can use what you learned in chapter 3 about how to solve matrix equations. I mean, actually, we don't really need to do it this time because we can just spot there is a solution. So we could spot that the solution is alpha is x plus y over 2 and beta is x minus y over 2. That is a solution to this matrix equation, and therefore every vector xy is equal to a linear combination of u1 and u2. But if you had a more complicated example, so an example where it wasn't at all obvious how to, or whether indeed it was possible to write every vector as a linear combination of certain other vectors, then you could write it as a matrix equation like we did here, and then solve the matrix equation using the row-reduced echelon form techniques for solving systems of linear equations. If you'd like to see an example of doing this where the equations were a little bit more complicated, you can see 4.7.3, example 4.7.3 in the notes for a more complicated example of showing that something is or is not a spanning sequence by solving some linear equations.